This is Physics 2120, Lecture 5, and today we're going to talk about electric potential. So last semester, after we talked about forces, we said we can solve some problems easier if we use energy. And so we developed the concept of potential and potential energy. So for example, the work done by a force is F dot ds, which is mg dot ds for gravity. As this is the work done by the gravitational field, the potential energy of the mass system is changed by amount delta U is equal to mg dot ds. For a finite displacement of the mass from A to B, then we would integrate that to get delta U, and we get mgh. In electricity, we also have a potential energy. So when a test charge is displaced in an electric field, it also experiences a force, which is QE. That force is conservative. Remember, ds is an infinitesimal displacement vector that's oriented tangent to the path that the particle takes through space. So the work done by the electric field, which remember is F dot ds, is just QE dot ds. So as this work is done by the field, the potential energy of the field and charge system is changed by delta U is minus QE delta S. For a finite displacement of the charge going from A to B, the change in potential energy is the potential energy at B minus potential energy at A is just minus Q times the integral of E dot ds. Now because QE is conservative, the line integral does not depend on the path taken by the charge. This is the change in potential energy of the system. The potential per unit charge, U over Q, is called the electric potential. The potential is independent of the value of the charge. And the potential has a value at every point in an electric field. So the electric potential, V, is U over Q, which is the electric potential energy over the charge. Now, potential is a scalar quantity since energy is scalar. So as a charged particle moves in an electric field, it will experience a change in potential. And that change in potential, which is the change in potential energy over Q, is just minus E dot ds, the integral. The difference in potential is the meaningful quantity. We often take the value of the potential to be zero at some convenient point in the field. Electric potential is a scalar characteristic of an electric field, independent of any charges that may be placed in the field. So, if we assume a charge moves in an electric field without any change in its kinetic energy, the work performed on the charge work is Q delta V. The units of volts is a joule per coulomb. It takes 1 joule of work to move a 1 coulomb charge through a potential difference of 1 volt. In addition, I can write electric fields now as both newtons per coulomb or volts per meter. That indicates that we can interpret the electric field as a measure of the rate of change with position of the electric potential. Another unit of energy that's commonly used in atomic and nuclear physics is the electron volt. 1 electron volt is defined as the energy a charged field system gains or loses when a charge of magnitude E, an electron or a proton, is moved through a potential difference of 1 volt. So 1 electron volt is 1.6 times 10 to the minus 19 joules. Now, what about the potential difference in a uniform field? Well, the equation for electric potential can be simplified if the electric field is uniform. Remember, this can only be applied if the electric field is uniform. If that's the case, then delta V, which is the integral of E dot ds, well, E is constant, so it comes out of the integral. And so the potential difference is minus E times d, as the distance the charge has moved in the electric field. And the negative sign indicates that the electric potential at point B is lower than at A. So when the electric field is directed downward, point B is at a lower potential than point A. So when a positive test charge moves from A to B, the charge field system loses potential. Of course, if it loses potential energy, it's going to be gaining kinetic energy. Just like this was, maybe we could pretend that this is a gravitational field. And instead of electric field, we just call that G. Then if I had a ball of mass M, if it goes from position A to position B, it has lost potential energy. It's the same concept. So a system consisting of a positive charge and an electric field loses electric potential energy when the charge moves in the direction of the field. An electric field does work on a positive charge when the charge moves in the direction of the field. So that charged particle gains kinetic energy equal to the potential energy lost in that charge field system. This is an example of conservation of energy. If Q is negative, then delta U is positive. A system consisting of a negative charge and electric field gains potential energy when the charge moves in the direction of the field. In order for a negative charge to move in the direction of the field, some external agent must do positive work on the charge. Now, if I look at this electric field, point B is lower in potential than point A. And point B and point C are at the same potential. We give the name equal potential surface to any surface consisting of a continuous distribution of points that have the same electric potential. So let's look at an example. A positive test charge is released from rest and moves in the direction of the electric field. The change in potential is negative. Therefore, the change in potential energy is negative. And force and acceleration are in the direction of the field. Well, let's look at this example. A battery produces a specific potential difference, delta V, between conductors attached to the battery's terminals. A 12-volt battery is attached between two parallel plates. The separation between the plates is 0.3 centimeters. If the field is uniform in between those plates, what's the magnitude of the field? Well, in this case, the electric field is uniform, so we can say the potential difference is equal to the electric field times the distance between them, or electric field is V over D. Well, delta V, the potential difference, we said was a 12-volt battery, and the distance between them was 0.3 centimeters, and so we get 4 times 10 to the third volts per meter. Let's go back to this problem. A proton is released from rest in a uniform electric field of 8 times 10 to the fourth volts per meter. The proton undergoes a displacement of 0.5 meters in the direction of the electric field. What is the change in potential from A to B? What is the change of potential energy of the proton from A to B? And what is the speed of the proton at B? Let's look at these one by one. This is a constant electric field. So then we can say delta V, which is minus E times D, is minus 8 times 10 to the fourth times 0.5 meters. And then I get that the change in potential in that 0.5 meters is negative 4 times 10 to the fourth volts. So now, how do I get the change in potential energy? Well, change in potential energy is just charge times the change in potential. So in this case, it's 1.6 times 10 to the minus 19 coulombs, the charge of a proton, times our voltage. And we get a change in potential energy of minus 6.4 times 10 to the 15th joules. So to calculate the speed, we know that the change in potential energy has got to equal the change in kinetic energy, which is just 1/2 mv squared. And so I solve then for v. v is the square root of 2 delta u over m. I plug in my numbers, and I'm going to get 2.8 times 10 to the 6 meters per second. Now, a positive point charge produces a field directed radially outward. And the potential difference between 2 points A and B, remember it's path independent, so it's only going to depend on our endpoints, which we know are only going to depend on how far away I am. So, VB minus VA is KQ times 1 over RB minus 1 over RA. So the electric potential is independent of the path between A and B. When using point charges, it's customary to choose a reference point of the potential equals 0 at R equals infinity. Then we can find the potential at any point R is just KQ over R. So I can plot then the electric potential in the plane around the charge. The red line here shows the 1 over R nature of the potential. The electric potential due to several point charges is the sum of the potentials due to each individual charge. This is an example of the superposition principle. And now, instead of when we figured out electric field from point charges, we had to do the vector sum of all those electric fields. For potential, all we have to do is the algebraic sum, or add up K times the Q over R's. And this gives V equals 0 at R equals infinity. So, if I wanted to figure out the electric potential of a dipole, that's a positive and negative charge existing next to each other, that graph shows that potential of the dipole. And there's a steep slope between the two, and the slope of this graph shows us the strength of the electric field. Now, if I wanted to find the potential energy of multiple charges, I consider first the two charged particles. The potential energy of the system is K Q1, Q2 over the distance between them. If the two charges are the same sign, U is positive, and work must be done to bring the charges together. If the charges had opposite signs, U would be negative, and the work is done to keep the charges apart. If there are more than two charges, then we find U for each pair of charges and add them. So, for 3 charges, then, the potential energy is K, and then we have Q1, Q2 over the distance between them, and Q1, Q3 over the distance between those, and Q2, Q3 over the distance between 2 and 3. The result is independent of the order that you add these charges up. Now, to get V from E, we had to integrate the electric field along a path. The inverse of that, of course, is taking a derivative. So if I want to go from E to V, let's assume, for example, that E has only an x component. Then E sub x is going to be the derivative of V with respect to x. Of course, I'm going to have similar statements to the y and z components. Equal potential surfaces must always be perpendicular to the electric field lines passing through them. So, if I have an infinite sheet of charge, we said the electric field is uniform and is directed out. The equipotential lines are these dashed blue lines. The electric field lines are the brown lines. And the equipotential lines are everywhere perpendicular to the field lines. The same thing happens in a point charge. Point charge, of course, the electric field lines are the brown lines that go radially outward. The equal potential lines have to be perpendicular perpendicular everywhere to the field lines, so they have to form spheres, spherical surfaces around the point charge. Or in a dipole, the brown field lines again are the electric field lines, so the equal potential lines have to be perpendicular to those, and we see those are kind of concentric ovals or concentric circles around these point charges. Now, in general, the electric potential is a function of all three dimensions. So if I have a potential that's a function of both x, y, and z, you can find all the components as partial derivatives. So e sub x is the partial of v with respect to x, and e sub y is minus the partial of v with respect to y. A partial derivative just means that you treat all variables as constants except for the one that you're really interested in. So for example, say I had a function that was a function of both x and y. Let's say it's 3x squared y squared. The partial derivative of f with respect to x is going to be 6x y squared. I treated y just like it was any other constant and just took the derivative of x. So let's consider this, and let's look at this problem of a field due to a dipole. We want to find the electric field at point P, where point P is on the axis that I have my charges on. And what is V in the electric field if x is much bigger than A? Well, we start with the idea that potential is K times the sum of the Q over R's. So in this case, it's going to be K times positive Q over x minus A. That's this distance right here, x minus A. And then it's minus Q, and the distance there is x plus A. So we get a common denominator, we multiply, so we can pull the Q out, and we get an x plus A minus x minus A over x squared minus A squared. We simplify this and we get that V as a function of x is 2kqa over x squared minus A squared. We know that electric field is minus the derivative of V with respect to x, or E is minus the gradient of V if it was in 3 dimensions. So we need to take the derivative. Well, it's x squared minus A squared to the minus 1. So the derivative of that is going to be minus 1 times x squared minus A squared to the minus 2 times the derivative of what's inside, which would be 2x. So then the electric field as a function of x is 4kqax over x squared minus A squared, quantity squared. Now I could have calculated this electric field just by figuring out the electric field due to the point charges and adding them algebraically, or adding them vectorially, but we did it using potential. It's just another way of calculating the potential. But now, what happens if x is much, much bigger than A? So, x squared minus A squared essentially becomes x squared. And so the potential becomes 2kqa over x squared. And the electric field becomes 4kqa over x cubed. So let's review what we talked about today. Electric force is conservative. If we have a conservative force, we can develop a potential energy function where the potential energy is just the integral of QE dot ds. We said we don't like dealing with a test charge, so let's figure out the electric potential, which is the potential energy per unit charge, just minus the integral of E dot ds. Or, conversely, the electric field can be obtained from the potential as the derivative of the potential.